All right, thank you. Well, it's great to be here again. I was actually there on that very first GPU day in 2010, so very nice that it's been, well, 10 years already. It's crazy. Well, I hope that next year we'll be there in person again, but, well, we have to do just online now. What I would like to talk about with Ernu from Wigner will be our Hastlayer project and how we made it support the latest Xilinx Alveo data center accelerator cards. But the Hastlayer project you will learn about in a minute. But just a bit of introduction before that, I'm from a company called Lombic Technologies. And in day-to-day, we are actually doing web development mostly with an open source content management system called Orchard. System, and we are serving customers all around the world with it, mostly in North America. And we are worldwide market leaders in that, working with companies like Microsoft itself, or the event organizer Fortune 500 company Live Nation, or institutes like the Smithsonian Institution. And we are glad to be a longtime partner of Wigner. And when we are not doing some web developments, then we are doing some research and development, like our Hastlayer project. First, in this talk, in the first half, I will talk about Hastlayer and the problem we are solving with it in general. And then in the second half, Ernu will talk about all the details behind the scenes, how the hardware engineering part happened here, because there will be some hardware engineering too. And a third colleague of ours, David El-Saig, also took part in this project, but he won't present today. But first, talk about you. Well, you're doing some number crunching, all right? And by number crunching, I mean something like AI, machine learning, or something with imaging, the image and video processing, or even computer vision. Or perhaps you are doing algorithmic trading on the stock market, like high-frequency trading. Or you have some kind of application where there's a lot of data compression. Or, well, fitting the event, maybe you are doing or specifically working with physics problems. Well, then you have some kind of algorithm, and probably you want to make it faster. So what can you do to make it faster? Of course, you can profile the code and optimize it. That would be the first simple step. Nothing. Naturally, you can parallelize it. So make it aware that there are multiple cores and a CPU nowadays, of course, so make it run in parallel. And obviously, you can also use faster hardware or more hardware. Now, let's pretend that you have done all of these already. What else can you do? Well, we are a GPU day, so of course, you can do some heterogeneous computing approaches. You can use compute accelerators like GPUs or FPGAs. Well, let's talk about that last part, FPGAs, a bit more, because that's interesting, I think. Well, what are FPGAs? Probably a few of you here heard of FPGAs before. If not, a very quick introduction. FPGAs are, or field programmable gate arrays, are pretty much chips that can behave like any other computer chip, of course. So that means that they can be dynamically configured. Now, if you have used Bing, as you can say, you Google something on Bing, then, for example, you have used FPGAs before already, because Bing is accelerated by FPGAs for a couple of years. Or if you have utilized the Azure cloud computing provider by Microsoft, then you have already used FPGAs too, because FPGAs are used smart network interface cards. Or if you had used some medical imaging devices like X-ray machines, MRI machines, do sometimes also have FPGAs in them for compute acceleration, just as sometimes even household appliances like routers or self-driving vehicles. The thing with FPGAs, though, is that it is a piece of logic hardware. You are creating a piece of hardware engineer to utilize them. And why would you do that? Why would you use an FPGA? Well, the reason is that they have some unique merits when it comes to compute acceleration. So let's compare different computing devices on a few factors. So let's talk about CPUs, GPUs, and FPGAs. Just a very, very quick, very rough overview, totally non-scientific, just to give you a basic idea here. So in a consumer CPU, you have maybe 4, 8 cores, in 16 nowadays for the high-end ones. For server CPUs, you have 32, 64 cores, but that's about it. With GPUs, they are on the other extreme. GPUs have thousands of cores. Of course, those are different cores, but still, you can run thousands of threads there. And with FPGAs, it's kind of FPGAs don't really have cores. However, that's not entirely true nowadays. But still, the degree of parallelism you can achieve on an FPGA is roughly in the order of magnitude of hundreds. Of course, all of this greatly depends on the specific chips, specific devices, and the specific applications. But this is just to give you a rough idea. Now, let's also talk about the complexity of programs you can run on these devices. So, of course, they win here because if it's a piece of software, you can somehow run it on a CPU, possibly with emulation, but still. Now, with the GPUs, it's the other extreme again, but the lower end here, because GPUs are much more limited computing devices. And FPGAs are kind of in between again, although you don't really run a program on an FPGA usually. Still, or implements on an FPGA are, I would say, somewhere in between. However, power efficiency is where FPGAs really shine. I would say that CPUs and GPUs are roughly on the same level here, again, greatly depending on a lot of factors, but FPGAs are really power efficient. And the reason is that with an FPGA, you are not writing a software for a processor, but rather you are kind of creating a processor architecture specifically for your problem. And that means that it can be very power efficient. And there is no instruction set to handle. There is no operating system to run, no other programs to execute. So an FPGA just computes what you need to be computed. But there is a big downside, and that is that it's very hard to develop with FPGAs, usually. Because programming CPUs is easy enough. GPUs a bit harder, but still it's programming. But FPGA development is something completely different. It's not software development, but it's hardware development. So you have to think in terms of, you have to think in very low-level terms, like gates and clock cycles. It's completely different than software development. So that sounds good. FPGAs are probably useful, but what is Hastlayer then? Well, Hastlayer is a tool that takes a computer program and turns it into an FPGA logic. For all the initiated here, we could also say that it's a software developer-aimed high-level synthesis tool. We could also say that Hastlayer takes a computer program and turns it into a computer chip. Or we could also say that we take some logic which is expressed as software form and turn it into another piece of logic, which is expressed as hardware form. And not just any software, actually, we are talking about the .NET platform. Probably most of you here have worked with the C++ or Python before. That is also available, although the primary languages of .NET are C# and Visual Basic. But you can also use functional languages like F# or scripting languages like PHP or JavaScript even. So all in all, what we are aiming for here is getting the computing benefits of FPGAs for all software developers. So FPGAs and Hastlayer is not a silver bullet, but if we are talking about compute bound, so CPU bound algorithms, which can be, then you can get a very substantial performance increase with FPGAs and with Hastlayer. And at the same time, you get a higher power efficiency. So you can compute more things with less amount of power. And if you are thinking about algorithms that run on dozens or hundreds of servers, usually that power efficiency gain can be a huge cost saver. In data centers, as I'm sure the previous colleagues here can confirm, power usage is one of the primary costs, power and cooling. But with Hastlayer, the whole thing is still software development as usual, so no hardware engineering knowledge required here. And we actually have some quite nice results already. These are some preliminary benchmarks for the Alveo cards, so we expect these to be much, much better still. We have tested a couple of algorithms which are available open source in the Hastlayer SDK, and all of the results and the details how we got there are also available online, but just a quick recap here. Usually we see some kind of performance advantage to comparable CPUs. Even on the small and cheap Nexus boards, you get a performance advantage compared to a comparable CPU, and power consumption advantage as well. The orders of magnitude better power consumption for the same computation. And with the Alveo cards that Erno will talk about in detail, you also get multiple times of the performance increase as well as the power consumption decrease. But enough talk for now. Let's see a demo. And now I switch over to Visual Studio, which is the development environment that but you can use any development environment. I will just show you a little bit of code. If you are not a developer, not very, it was super simple. What we are looking at here is an algorithm called, well, parallel algorithm, and as you might have guessed from the name, this is a highly parallelized algorithm. This is just a synthetic example of the classes of algorithms that are suited to be accelerated by Hastlayer. So this is not a real-life example, just to give you what's efficient here. And what this algorithm does, the core of the logic is here. It does a bit of conditional logic to simulate something like that, which is executed 10 million times. And this whole thing is actually executed in multiple tasks. You can think of tasks, this is a .NET notion here. You can think of tasks as threads for now. So basically, we are starting threads here. And we are starting this many threads. Oops, sorry, I misclicked. And this many threads are 260 threads. So we are starting 260 threads, which will be executed all in parallel. Now, why are we doing this? Why 260 exactly? Because that many will fit on this FPGA board that I have here for the demonstration. This is a Nexus board. The type of the board is called Nexus FPGA. And why I'm talking about the FPGA, because when we convert this whole algorithm into a hardware implementation with Hastlayer, then on the FPGA, we will get 260 little cores. So for each of these threads, we will have a parallel execution unit there. We will get an actual hardware level parallelism of 260. Or we could also say that we are dynamically generating a CPU or a processor that has 260 cores. Whereas when I execute the whole thing on this PC that I'm running this from, these 260 threads will, of course, run still on these couple of cores of the CPU. In the case of my CPU, there will be 4 physical cores and 8 logical cores. So the level of parallelism we'll get is much, much, much smaller. Actually, they'll take care of not to oversaturate the CPU, but still these 260 threads won't run at the same time on those just 8 cores. It will try to optimize it for performance, but of course the level of parallelism will be very, very low compared to the FPGA. And now let's also run this. This is part of a small console application that I will now execute. The API of Hastlayer is quite simple. All of this is up on GitHub, so you can check it out in detail. What happens now is that Hastlayer generates the hardware implementation for the FPGA. And once that is done, it will start communicating with this device I have just shown you here. First, it will execute this as software, just so we can have a comparison. And then it will execute it as hardware. So let's see. This took about 3 seconds, give or take. Although this is a very rough measurement because my computer is doing a lot of other things, etc. So this can be smaller, but just to give you an idea. And on the hardware, it took about 300 milliseconds. If we are talking about just the hardware execution, or about 400 milliseconds if we also take the relatively slow communication round trip into account. So that means that the FPGA is faster even on this cheap low-end board here. And actually, if you take a look, on the hardware, it took exactly the same amount of time each 3 times, down to the 10,000th millisecond. And this is, again, because there are no noisy neighbors, no other software to run, no operating system. It just computes what you need to be computed. That was a quick introduction. And now I will hand over to Ernő, so he can also talk about the details of our Alveo implementation and Alveo support specifically. So, Ernő, up to you.
Okay. Good morning. I am Ernő Dávid from Wigner Physics, where I work as an FPGA developer. Points why is a high-level synthesis tool like a Hastlayer can be interesting for the software developers. Now I want to start with another one, why Hastlayer can be interesting for the FPGA developers too. In Wigner, in the data acquisition laboratory, we develop a hardware and firmware for physical experiments, like, for example, Alice experiment in CERN. And we found for these tasks. As you can see on the left side, in the 80s, the physicists and the electrical engineers built digital designs from discrete components soldered to a PCB. But nowadays, with FPGAs, it's much easier. You put one or more FPGA in the middle of the board with few necessary external components around, and you can implement a wide range of digital designs without any solder. Let's look inside the FPGA. On very basic level, we have small logic blocks with flip-flops to store the binary values, and with lookup tables to implement combinational logics. These logic blocks organized in 2D arrays with a routing fabric between them, which allows to make a connection between any two logic blocks. A very important concept here that in every clock cycle. This is the biggest difference between the software executed by the CPU step by step versus a digital design. On CPU side, the instruction sits in the memory until one of the CPU cores executes them. But in the FPGA, you can utilize all of the flip-flops, millions of them, for your task if you find a way. This basic layout remains same in the last 30 years. We get more and more resources, like the Xilinx Alveo data center accelerator cards. Our main target card is the U250, and this will be present in the Azure. It contains 1.7 million lookup tables, which means in this case 3.4 million flip-flops. And for some time, we have even more complex digital parts integrated in the fabric, like the flip-flops. For example, we have digital signal processor, internal memory blocks, gigabit transceivers for high-speed protocols like PCI Express and optical Ethernet, and memory controllers, and so on. You can see that we have Alveo cards with up to 64 gigabit DDR memory, or we have variants with 8 gigabit HBM2 memory with quite impressive memory bandwidth parameters. The Alveo cards connects to the CPU over Gen 3 16-lane PCI bus, like the GPU cards. And there is even 2 QSFP connector on the board, so it can behave like a 100 gigabit Ethernet card also. In early days, in 80s and 90s, the developers were able to design the routing on paper and connect the few logic book by hand. Then later, the tools started to use schematics to capture the design, which is still usable today until certain complexity. The hardware description languages like VHDL and Verilog also appeared in 80s, but for a long time they were used only for simulation and verification for ASIC digital designs. But with time, the FPGA vendors adapted also for the synthesis. And currently, this is the most common way to implement digital designs in the FPGAs, especially when you're dealing with low-level protocols or with fast data acquisitions, when the exact timing is mandatory. But the increase in the FPGA resources allows us to move even more complex functionality into the FPGA, like why to send data to a powerful server for analysis when it can be implemented inside the FPGA in real time. The only problem that implementing a complex scientific calculation in VHDL on flip-flop levels is very slow and error-pruning process. It's like implementing a web content management system in CPU assembly language. So there is an increasing need and opportunity in the FPGA development for high-level synthesis tools like where you can use an algorithm developed and tested in a high-level CPU language like C, C++, C#, inside the FPGA with ease. This is one of the reasons why we started to collaborate with Lombik in Hastlayer project 2 years ago. First, we started to implement the support for Microsoft Catapult platform, which was presented last year by Zoltan at this very same event. Working version for the Xilinx Alveo cards. Okay, let's go back to the software side, and let's play with the idea that to accelerate our .NET application with a Hastlayer generated core, VHDL core. Of course, this is just a theoretical exercise, since you will get a pre-built system as a Hastlayer user. Let's FPGA card sitting on your desk, and it's connected to the PC through USB or TCP/IP protocol. The basic operation of the Hastlayer acceleration that you send your input data from the .NET application to the FPGA card. On the FPGA card side, we need a so-called hardware framework around the Hastlayer generated core, which stores the data in the DDR memory, invokes the core, sends the results back to the .NET application. How the first Hastlayer version implemented, and which was Zoltan just demonstrated. Okay, let's move to the Xilinx Alveo card execution environment. Since we are at a GPU day, I am happy to inform you that Xilinx adopted the OpenCL API for their Alveo card development. Your .NET application communicates with the OpenCL API through the Hastlayer software parts. And on the FPGA side, the Xilinx provides the so-called shell, which manages the memory movement between the CPU memory and the kernel invocation. Typically, the OpenCL kernel is written in OpenCL language, but since in this case, the target is an FPGA, the Xilinx tools allows us to provide the kernel source in the VHDL language, the generated core by the Hastlayer SDK. This is the so-called RTL register transfer level kernel option. We faced several challenging areas, and I want to mention a few of them. The first is the memory access. In the Hastlayer generated core, our internal memory bus is 32-bit wide, while the external memory bus can be between 32-bit and 1024-bit wide. Initially, we started a 32-bit external memory access, which resulted in rather poor performance. I will present some results on. Later, we implemented a small cache system built from flip-flops to speed up the memory read and write requests. And we are also playing with the idea to add the second level cache system built from internal FPGA memory blocks. We used our image processing algorithm sample to measure the impact of the cache system. This is our most we implemented different kernels with different AXI data bus width and cache width, and we tested the DDR memory and the HBM memory too. At first, we tested it in 32-bit mode, which means no cache, and found that the DDR memory only slower by 12% than the HBM memory. Better performance with the HBM memory. But it seems that in this case, the single DDR memory channel versus single HBM memory channel nearly behaves same. But when we started to increase the AXI data bus width and the cache width, we managed to gain significant speed up with maximum AXI bus width 7 and 8. Finally, we settled with the 512-bit because we found that 1024-bit causing kernel frequency drops in some test applications. Yeah, the second challenge which I mentioned, the kernel frequency, to utilize the abundant resources in the FPGAs, parallelism from our algorithm as much as it's possible. But this means that we have to distribute our input data to millions of flip-flops, and after the calculation, we have to collect them. And this means bigger and bigger combinational logics for multiplexing and demultiplexing the data. And bigger combinational logic means longer propagation delay, which means lower kernel frequency. Currently, and in certain cases, we observe a frequency drop above certain parallelization level. There are techniques to solve this, to inject flip-flops in the combinational logic network, to split them into smaller parts. This will produce a few clock cycle delay in the result, but the gain from the overall higher kernel frequency is much more important. Currently, we are the last change which I want to mention is the build time. It is actually not a Hastlayer issue, but Alveo card, or better to say, a generic FPGA feature, FPGA development feature. Even the simplest design, 4 hours to build. The reason for this that the whole design is rebuilt every time when you change something, because usually you have to reconfigure the whole FPGA fabric to run a new design. It's like recompiling the whole operation system to run your application on the CPU. Of course, the existing FPGA configuration can be loaded immediately. There is a technique configuration, which is something like dynamic loadable libraries on the CPU, or like hot plug expansion slots on the memory, on the modern motherboard. Some area in the FPGA fabric can be prepared for dynamic replacement. In our case, this would be the kernel area. So if you change something in your .NET assembly, then you need just to rebuild the kernel part. This feature is already supported by the law, but not in the Alveo card development flow. But there is a promise that this will be added in the future. While we are working on the Alveo card version to further improve, we are also looking for other areas where it would be also useful. Namely, we are thinking to develop support for the Xilinx Zinc family, where in the FPGA fabric, an ARM CPU is also integrated with capabilities even to run a Linux. This FPGA family already on board of drones and satellites in aerospace industry, because it is very handy to run your higher level controlling algorithms on the ARM CPU and put the hardware related digital logic in the FPGA fabric. We think that if there is an image processing required, then we can accelerate it with the Hastlayer in a competitive way. For this move, we need the industry standard AMBA AXI interface support, which is the Alveo card version. So we are optimistic about this plan. Okay, thank you for your attention. We are happy to answer your questions now, or you can get in touch with us via the links on this slide.
So thank you, and Zoltán. So it's time for questions for both of you. Maybe you can see.
Hi, my first question is, which is the cheapest FPGA platform, for example, for a student to try this Hastlayer?
Thank you for the question. These boards, in my part, probably Xilinx academic program. So this is not manufactured by us. Just to make clear, we are using off-the-shelf hardware, but I think this would be the cheapest. is something that you have to actually purchase, even if it's for a reduced price. You can also use the cloud options with the various Alveo cards that Erne mentioned for $1 to US per hour if we are talking about just shorter tasks.
Make parallels the programs, it is a good practice, and also to over efficiency. But I work on embedded system, and the timing is very important. The Hastlayer is support this real-time aspect of the FPGA using.
Let me also this question to you. That's quite interesting question. This real-time usage is not something that we specifically support or specifically designed Hastlayer for, but it is actually it would actually be possible with the Xilinx platform that Erne talked about the aerospace applications. So right now, the model that you use Hastlayer in is that you have some kind of program running on a CPU or a whole load parallel computations to an FPGA. So we are using an FPGA as an accelerator, a compute accelerator. You are right that FPGAs can very well be used for real-time tasks, since, as I also shown, they are deterministic, since there are no noisy neighbors on the same chip. What would be possible in the very near future, as we are implementing support for embedded systems, is talking to peripherals directly from the FPGA chip. So you wouldn't go through the CPU, kind of break the real-time promise, because we are talking about higher level operating systems there, but rather you would directly communicate with other peripherals on the chip or off chip from the FPGA, making the whole computation real-time.